Good day and welcome back to part 3 of our discussion on related rates. In the previous videos, we've introduced the overall procedure or thought process that we use to approach and solve these problems, as well as seeing several standard techniques. In this video, we will focus in on a single problem and see a slightly different technique than our previous problems. So first, reading through. A water tank has the shape of an inverted circular cone. So think an inverted circular cone. So a cone, think just like kind of an orange parking cone. And the fact that it's inverted just means that it's angled in such a way that you could imagine filling it up with water. So we have this circular cone. We are told that its base radius is 2 meters. So the radius at the base is 2, and it has a height of 4 meters. So water is being pumped into this tank at a rate of 2 cubic meters per minute. What we would like to do is find the rate at which the water level is rising when the water is 3 meters deep. So in this tank, there's a certain amount of water, so some associated water level. Water is being pumped into the tank at a certain rate, and we want to know how quickly is that water level rising. And what that means is we need to introduce some notation specifically related to the water portion of this tank. So I'm going to go ahead and I'm going to let R represent the radius associated with the water level, and we'll let H represent the height of the water in the tank. Let's think about what we know and what we want to find. What we know is that water is being pumped in at a rate of 2 cubic meters per minute. So take a minute, pause the video. What rate of change is that describing? Think about the units. Because the units are measured in cubic meters, those are units for a volume. So what this is telling us is that the rate of change of the volume, dV dt, is going to be 2 cubic meters per minute. And what we would like to find is dH dt. Specifically, how quickly is that water level rising, i.e. the rate of change of the height, when H 3. So what we need at this point then is an equation relating the volume to the height. So when it comes to a cone, we've probably encountered this formula in the past. So take a moment and think, what is the formula for the volume of a cone? And the desired formula is 1/3 pi r squared h. And for what it's worth, how I remember this is the volume of this cone is 1/3 of the volume of the cylinder that it contains. That is to say, kind of hidden in this picture, there is a cylinder. And the volume of the cone is 1/3 the volume of that associated cylinder. So I'm throwing that out there just in case that helps you to remember this formula, because now that we've seen it, it's certainly something that's fair game for us to see again. Now what we need to do is think about how we can differentiate this implicitly. But there's an issue. What is the difficulty you might see at this point? We know dV dt, we want to find dH dt, so how in the world do we handle this R? It's as though we have this extra variable in here, which is complicating the situation. So what we would like to do is see if we can somehow rewrite that radius so that it's in terms of the height or the volume. And in order to do so, we're going to pull a key fact out from our picture. Notice in our picture we can see two right triangles. The one associated with the larger entire cylinder and the one associated with the water level. Drawing this separately, we have this larger right triangle, and then sitting inside this larger right triangle is a smaller one. And this gives us two similar triangles. And remember, when you're comparing similar triangles, the ratios of their side lengths are going to be equal. That is to say, R over H, looking at that smaller inside triangle, will be equal to 2 over 4. So R is equal to 1/2 of H. And that allows us to rewrite this troublesome R quantity in our formula. And that is the key step in difficulty in this problem, seeing the fact that we have these similar triangles that allows us to simplify our formula. And it is worth noting that if you write down your equation like we've done here, and there's some variable that you do not know anything about its rate of change, think about, is it possible for me to rewrite that quantity? So in this case, rewriting, we have the volume is equal to 1/3 pi times R, which is 1/2 H squared, times H. So this would be 1/3 pi times 1/4 H squared times H, or the volume is 1/12 pi times H cubed. And we are now in that ideal scenario. The two quantities we want to work with, V and H, we have an equation relating them. So we differentiate both sides implicitly with respect to t. On the left-hand side, we have dv dt. On the right-hand side, we would have, what, pi over 12, a constant, times 3h squared. And note it's an implicit derivative, so we multiply by dh dt. dh dt is the quantity that we want to solve for. So if we go ahead and we isolate dh dt, so note the 3 would make that really a pi over 4 when we cancel. So we could multiply both sides by 4 over pi and divide by h squared. And if you do that, you would have 4 over pi h squared dv dt. And we are now ready to determine the desired quantity. dh dt, when h is equal to 3, would be 4 over pi times 9 multiplied by dv dt, which is 2. And simplifying this just a smidge, we can write this as 8 over 9 pi, and we should always include those units. So in this case, it's a rate of change of height. So height is going to be measured in meters, and our time units is measured in minutes. So the units would be distance over time, which in this case would be meters per minute. And this gives us the desired rate of change. As I've indicated multiple times in previous videos, related rates problems in particular are the type of problem that you really need to go through and practice. So if you have not already done so, go to the suggested problems, work examples, look through the examples in the book. Also, to help you along these lines, you can find an associated class worksheet in Canvas. I recommend taking that worksheet and scheduling yourself, a fairly large amount of time. There's 4 problems on it, so think maybe 30 to 40 minutes. And do as much as you can. In the next video, we will cover 2 of those problems, and you can also find full solutions on Canvas. But as usual, don't just look at the solutions or don't just go to the video. Spend the time and think about it first. That is the key step to learning and understanding the material. So stay tuned and take care.